Imagine standing on the lunar surface, gazing back through the vast, quiet emptiness of space, and beholding a view that challenges everything else in our solar system. There it is, a radiant blue orb encircled by twisting white vapors, shining brightly against the infinite darkness. It appears serene. It seems welcoming. It resembles a precious gem. Yet for a scientist studying the cosmos, this azure sphere isn't merely stunning. It's an enigma. It's a contradiction. According to every principle of physics and how planets come together, that water has no business being there. Our home is a world blanketed by liquid water over 70% of its surface. But we circle a star that's essentially a blazing nuclear reactor. We're positioned in a part of the solar system where intense heat ought to have evaporated all traces of water eons ago. Earth ought to resemble a desolate, baked wasteland like Mercury, or a powdery wasteland like Mars. Instead, we're surrounded by vast seas. This water shapes our planet entirely. It's the birthplace of life and the essence that sustains us. However, its source remains one of science's greatest and most debated puzzles. Could it have arrived via comet showers from above? Might it have seeped out from the planet's own crust? Or does it stem from an era predating Earth's formation? In this exploration, we'll delve into the beginnings of our oceans. We'll journey to the era of flames, the period of massive downpours, and reveal the hidden story behind the water in your cup. To grasp the puzzle of our seas, consider the planets nearby. The inner solar system forms a domain dominated by stone and intense heat. Mercury, nearest to the Sun, stands as a scorched, breathless expanse of iron and rock, seared by relentless solar energy. Venus, similar in scale to Earth, has become an inferno of overwhelming air pressure and unchecked warming from greenhouse gases, where any ancient water long since escaped as vapor into the void. Mars, the reddish world, endures as an icy wasteland with moisture locked away as frost in the poles or hidden far below the surface, a remnant of a once moister era. And then comes Earth. We're the outlier. To our knowledge, we're the sole planet in the cosmos where water persists in its three phases at once: solid ice, gaseous vapor, and, most vitally, flowing liquid. We're a realm defined by water, amid a space sector that's downright antagonistic to it. The quantity is mind-boggling. More than 1.3 billion cubic kilometers cover our exterior. It submerges basins up to 5 kilometers in depth. It etches out valleys. It permeates the air. It courses through every organism's bloodstream. Such profusion contradicts the classic theory of planetary assembly. During the turbulent, scorching vortex of debris and gases that birthed the solar system, the region near the nascent sun was far too warm for water to solidify. It would have been turned to gas, swept toward the system's fringes by stellar winds. Earth coalesced within this arid belt. It emerged from parched minerals in a barren area beneath a fiery star. Thus, when you gaze upon the Pacific Ocean, you're witnessing something that, by theory, defies possibility. It's an outsider element that inexplicably settled into a place not meant for it. Unraveling its arrival requires examining the unseen divide that splits our solar system. Experts have charted a hidden frontier in the void, a temperature divide called the frost line or snow line. It operates like frost around a nighttime bonfire. Near the flames, conditions are too warm for snowflakes to form. Water stays as steam or gas. But venture farther into the chill, and you pass a point where temps fall enough for water to harden into ice. In the solar system's infancy, this boundary lay approximately between Mars's and Jupiter's paths. All within, Mercury, Venus, Earth, Mars arose in the desiccated inner zone. The fierce warmth from the emerging sun drove off volatile elements like water. The particles that merged into our world were solely rocky and metallic, devoid of hydration. Yet past that line, in the frigid outer reaches home to the gas behemoths, water thrived. It solidified into durable, stone-hard ice chunks, creating enormous stockpiles in comets and frozen satellites. Per planetary formation rules, Earth occupies the incorrect territory. We sprang from the inner system's bone-dry particles, but were mantled in outer system ice. Our world's origin wasn't a calm gathering of materials. It was a savage, disordered clash of collisions. Some 4.5 billion years back, Earth expanded through accretion. Myriad asteroids, planetesimals, and chunks of stone collided relentlessly, drawn by their mutual gravity into an expanding ball. Every such crash unleashed vast kinetic energy, transforming immediately into scorching heat. The nascent Earth wasn't merely warm. It was a seething melt. Within this crucible of formation, any water molecules embedded in those primordial stones would have been driven off by the blistering temperatures of assembly. It would have vaporized, ascending as vapor and swept away by the savage solar winds from a fledgling sun, far more turbulent and ferocious than the one we observe now. According to prevailing theories, the early Earth was a barren, arid orb, a lifeless swirl of molten material amid a hazy disk of dust. It possessed an iron core and a silicate mantle, yet it missed the essential, fleeting compounds needed for life. No hint of azure adorned its surface. Transport yourself to that era, the Hadean Aeon, named after Hades, the realm of the dead in Greek myth, a fitting moniker. Gaze upon Earth some 4.5 billion years back, and it would defy recognition. Continents were absent. Verdant hues were nowhere to be found. Oceans did not exist. Instead, the exterior was a roiling, luminous sea of liquid stone, a worldwide expanse of lava that beamed thermal energy into the inky void beyond. Overhead, the heavens weren't cerulean. They were probably a murky, poisonous amber or crimson, thick with carbon dioxide, nitrogen, and atomized minerals. The air pressed down with overwhelming force. In this infernal realm, liquid water was inconceivable. Any H2O particle grazing the surface would evaporate on contact, escaping into the high layers above. This marked the starting line for our world, a fiery domain marked by the total lack of the fluid that today envelops it. Still beholding this incandescent globe, we sense an extraordinary shift was imminent. This inferno somehow needed to chill, and the desiccated mass to gain moisture. The shift from Hadean inferno to aqueous realm stands as the solar system's most profound evolution. As the fledgling Earth started to moderate its temperature, perhaps developing a delicate, tentative shell, fate struck with a cataclysm that wiped the slate clean. Enter the giant impact theory. It posits that roughly 4.5 billion years ago, Earth shared its path with a rival, a body the size of Mars dubbed Theia by researchers. The encounter was unavoidable. It struck the proto-Earth with unimaginable might. This wasn't just a strike, it was a fusion. The ferocity melted the world anew. It hurled countless tons of liquefied debris skyward, crafting a fiery disk that later congealed into our moon. For the tale of hydration, this juncture is pivotal. It was a purge. The impact's blaze was fierce enough to evaporate whatever tenuous gaseous envelope Earth had retained. Any pools, nascent basins, or merely moist surfaces vanished in a flash. Water's components were ejected into the emptiness, gone for good. Earth emerged reeling, tilting, and bone-dry. It was a hard reboot, ensuring a dehydrated origin. Following Thea's cataclysm, a deep hush descended on the solar system. The rubble dispersed. The moon found its groove. Earth embarked on a gradual mending. The once boiling, glowing magma sea dulled as warmth bled into the cosmos. Surface heat waned. A fragile layer solidified atop the flow. This became the initial crust, a rough ebony terrain of basalt and obsidian, prone to fracturing and plunging into the liquid below. Picture a realm of dark, vitreous plains beneath a dim, remote star. No whispers of breeze stirred, with scant air to carry them. No surf crashed. The sole sounds were the crackle of contracting stone and the profound subterranean groans from within. It was an arid, hushed, grayscale existence. The container stood prepared. The basin was shaped, yet it remained void. Our world drifted as a thirsty wasteland through the shadows, yearning for sustenance it couldn't summon alone. Moisture had to arrive from afar. It required transport. Then, around 3.9 billion years ago, the suppliers showed up. The solar system wasn't the orderly machine of today. Titans like Jupiter and Saturn were on the move, reshaping their paths in a cosmic ballet that destabilized everything else. Their colossal pull functioned as a cosmic catapult, flinging orbits of countless asteroids and comets from the frigid fringes inward, straight toward the sun, and squarely into Earth's trajectory. This period goes by the name of the Late Heavy Bombardment. Over countless years, the heavens rained down destruction. Our planet endured a relentless barrage of space rubble. These weren't mere pebbles. They were colossal slabs of stone and frost crashing into the barren shell with the explosive power of atomic bombs. From the ground below, the darkness overhead must have been a horrifying swirl of glowing trails and bursts. Yet, this wasn't mere catastrophe. It was a vital delivery. Those colliding bodies served as transporters, interstellar haulers packed with the essential element our world was missing. They carried volatile elements, solidified vapors, and, crucially, the frozen H2O that would one day paint the scorched orb in shades of azure. When researchers initially hunted for the origins of Earth's liquid bounty, their gaze inevitably shifted to the distant fringes of our star system. Out there, beyond Neptune's chill void, float the comets. These are the grimy ice balls of the universe, primeval survivors from the solar system's infancy, made up mostly of iced-over gases, grit, and aqueous frost. They make for stunning couriers. As a comet dives sunward, solar warmth awakens it, unleashing a dazzling vapor trail that reveals the hidden moisture within. For years, the prevailing view held that these wanderers sculpted our seas. It seemed utterly logical. Amid the late heavy bombardment, hordes of such frozen visitors would have been catapulted our way. Every collision would unload a huge cargo of frost, vaporizing on contact or strike to bolster the steamy shroud enveloping the nascent Earth. There was poetry in the concept, our vast waters as thawed comet cores, the lifeblood in our bodies cascading from the solar system's remotest, iciest frontiers. It painted Earth as an arid container gradually brimming via a stellar pipeline. But science craves proof, not poetic ideas alone. To confirm comets as the ocean builders, We needed to sample them directly, matching the molecular profile of terrestrial H2O against comet-sourced variants. Plain water isn't simply H2O. Its hydrogen can snag an additional neutron, forming deuterium, heavy hydrogen. The balance between standard and heavy forms serves as a unique marker, revealing formation sites and environments. In 2014, the Rosetta probe achieved an engineering feat, rendezvousing with Comet 67P after a decade-long pursuit across emptiness. It dispatched a probe, Philae, to the frosty exterior for vapor analysis. The findings stunned everyone. The comet's water was deuterium-rich with a ratio triple that of our planetary reserves. The profiles didn't align. Had comets akin to 67P supplied our seas, Earth's elemental makeup would be unrecognizably altered. This revelation dismissed comets as the main contributors. The picturesque hypothesis crumbled. Those grubby ice clumps might have dotted a bit of moisture sporadically, but they never stocked the reservoir. The real suppliers were more elusive, hailing from their stonier, less watery kin. The asteroids, more precisely, a group of primordial celestial boulders called carbonaceous chondrites. To casual observers, they appear as unremarkable drab pebbles. No icy gleam, no streaming comas, but cosmic facades can mislead. These boulders function like stellar absorbents. Their makeup teems with hydrated clays, compounds embedding water units deep within their mineral frameworks. Some hold as much as 20% water by mass. Originating nearer to Earth in the asteroid belt, a zone chilly enough to retain hydration, yet not to forge solid ice. These damp stones probably pelted us in uncountable numbers during the onslaught. They delivered no free-flowing or frozen water, but moisture bound in mineral form. Upon slamming into the surface, impact energy freed the H2O as vapor. It built gradually, not in a deluge, but through persistent buildup. Impact after impact, fragment by fragment, the seas arose from infused grit. This idea forms the late veneer theory. It posits our planet's watery hue as a superficial layer, a moist overlay ferried by stony vessels shortly after Earth's assembly. Long ago, the tale of water centered on importation. We figured the globe began parched, needing outside replenishment. Lately, though, a bold alternative has surfaced, upending the notion of a desiccated origin. Suppose the water never descended from above. Suppose it lurked within from the start. Enter the inside job hypothesis. It proposes that the primordial dust specks assembling into Earth weren't quite so arid. Even amid the inner solar system's blaze, H2O might have adhered to grains, sequestered in rocky compositions right from the outset. If that's the case, Earth came into existence already brimming with the promise of vast seas. During its formation, as gravitational forces compacted dust into stone and stone into a world, that hidden water got sealed away. It stayed confined within the mantle's scorching compressed layers, far below the surface, amid rock-enduring immense forces. Today's familiar oceans aren't some foreign layer splashed on top. They're the planet's own perspiration, exhaled from the moisture it's harbored right from the start. This perspective shifts how we view the terrain beneath us. Far from blocking water, the unyielding bedrock could serve as the planet's primary storage vault. The notion seems far-fetched at first glance. How could impenetrable stone retain moisture amid the intense temperatures and pressures deep inside Earth? To test it, Researchers replicated the mantle's infernal environment using a tool known as a diamond anvil cell. They positioned minuscule bits of minerals between the points of flawless diamonds and applied tremendous force. This mimicked the crush of hundreds of kilometers underground, all while lasers heated the samples to match the searing conditions. Their observations revolutionized our understanding of geology. In those brutal pressures, the minerals didn't simply fracture or liquefy, they transformed. They restructured into dense, high-pressure variants that functioned like atomic enclosures. Within those enclosures, space existed for hydrogen and oxygen atoms. The tests confirmed that under enough compression, stone behaves as an absorbent material. It draws in and retains water molecules right into its crystalline framework. It shows no signs of dampness and stays as hard as ever, yet on a molecular level, it's fully infused. This breakthrough unveiled a concealed realm, hinting at an immense body of water imprisoned in the rock underfoot. The decisive evidence emerged from a diamond, ejected by a volcano, straight from the mantle's depths. Embedded in that gem was a minuscule inclusion, a grain of ringwoodite mineral. This substance only crystallizes at 400 to 600 kilometers down, in the boundary region separating the upper and lower mantle. Upon examining that small blue fragment, experts discovered it held a notable water content, roughly 1.5% by weight. That percentage might appear modest, but the transition zone spans enormous volumes. Should the whole area consist of such ringwoodite, all saturated like this specimen, the calculations become mind-boggling. It points to a subterranean water reserve equivalent to 3 times the total water in every surface ocean. We're adrift atop a secret abyss. The Pacific, the Atlantic, the Indian Ocean, these are mere spills, surface trickles in essence. The real sea lies solid and fiery, entombed 400 kilometers below in a lattice of azure crystals. Now what brought this buried water to the light? The driving force was thermal energy. In its early days, Earth was a cauldron of geological turmoil. Radioactive decay and leftover formation heat roiled its core. This fueled eruptions on an unimaginable scale. Countless volcanoes, cracks, and outlets scarred the hardening shell. When magma ascended from the mantle, the confining pressure eased. The water bound in the deep minerals broke free. It vaporized instantly. Over eons, eruptions didn't merely pour out molten flows. They belched fumes. They released quadrillions of tons of water vapor, alongside carbon dioxide and nitrogen, high into the air. This event marked the grand degassing. Earth was, in effect, venting its seas through sweat-like exhalations into the air. Clouds gathered into a dense shroud. The moisture had escaped the stone, but hadn't settled yet. It lingered overhead, encircling the globe in a steamy sheath, poised to descend. The scene was primed for the downpour. Yet before any rain could begin, Earth endured a prolonged, stifling impasse. Its air wasn't the airy, clear shroud of modern times. Instead, it formed a smothering, heavy cloak of water vapor, carbon dioxide, and eruptive gases. Surface pressure soared, possibly hundreds of times today's levels, a colossal pressure cooker. Weather as we know it was absent. Only endless, glaring opacity prevailed. Sunlight diffused into a hazy luminescence, veiled by layers of scalding mist. Heat lingered perilously, sustained by the steam's self-reinforcing greenhouse trap. It resembled a realm in stasis, a world paused in tension, anticipating relief from the blaze. The water existed, countless billions of tons of it, but it hung, ensnared aloft, unwilling to meet the soil. Earth teetered in a deadlock, space's chill pulling outward, the searing underbelly pushing back. Cooling was bound to happen, though gradually. Thermal energy dissipated into the void and the upper air's chill deepened. Eventually it passed a pivotal point. The molecules of water vapor, energized by heat over eons, started to lose momentum. They gathered and transformed. Up in the stratosphere, initial clouds emerged, not the light, cottony ones of a clear afternoon, but massive, ominous storm systems blanketing the planet. Then came the pivotal moment. One water droplet formed around a particle of volcanic ash. It became dense enough to defy the rising thermal currents beneath. It plummeted, descending through layers of steam thousands of meters thick. It withstood the intense warmth and collided with the rough, obsidian-like basalt below. No splash occurred. The surface remained scorching. Instead, it met the rock with a sharp sizzle, vaporizing on contact. This pattern persisted for ages, a misty precipitation that never reached the earth. An illusory downpour, yet the terrain was gradually yielding. Every droplet that struck and boiled away siphoned off a small amount of the Earth's heat. Bit by bit, sizzle after sizzle, the crust tempered. At last, a droplet touched down and lingered. This marked the close of the barren era. Once underway, the process accelerated without pause. What followed was an epic flood beyond human scale. It wasn't a shower lasting days, weeks, or even months. Scientific simulations indicate that after the atmosphere tipped into chaos, the downpour raged steadily for up to 10,000 years, possibly stretching to 1,000,000. A torrent of mythic intensity unfolded in solitude, unobserved by any eyes. Picture the ceaseless thunder of rain battering stone, a roar without respite. Through endless days and nights across millennia, bolts of lightning would streak the murky, vapor-shrouded heavens, briefly revealing a terrain being scoured anew. This wasn't mild, pure precipitation. The drops were warm and corrosive. Passing through the CO2-laden air, they picked up carbon dioxide, morphing into carbonic acid. They didn't merely rinse the surface, they eroded it. Carving into peaks and gouging troughs, the acid stripped away salts and minerals from the outer layer. It amounted to a fierce, geochemical cleanse, a worldwide rite that purged the remnants of the Hadean Eon. Where did all that liquid accumulate? Back then, the planet lacked familiar landmasses. No verdant fields or towering ranges to trap the flow. Instead, it featured a rugged, disordered expanse of eruptive summits and enormous low depressions from the late meteor strikes. Gravity dictated the path. Water cascaded toward the lows, gullies turned into rivulets, rivulets swelled into furious flows of hot, ashen slurry. Those flows merged into mighty waterways. They surged into the vast depressions, the wounds from primordial collisions. Initially, they formed mere simmering shallows at crater floors. But the deluge persisted. The pools linked up, grew profound, and engulfed the surroundings. Volcanic expanses sank beneath the waters, steaming as they solidified into pillow basalts amid the advancing flood. Gradually, relentlessly, the dark stone vanished under a swelling shroud of slate-colored waves. The molten sea gave way to an aqueous one. Eventually, the overcast parted and sunlight filtered through the clarifying air, falling not on a fiery orb, but on a transformed realm. a scattering of isles amid a worldwide steaming expanse. The precipitation ceased at last. The overcast dispersed, allowing the sun to emerge. Yet the vista it unveiled bore little resemblance to today's Earth. Stationed atop a solitary volcanic spire jutting from the swells some 3 to 4 billion years past, you'd gaze upon an otherworldly expanse. The sea wasn't azure. It held a thick, murky olive tone. Loaded with iron in solution, the fluid took on that shade. In contemporary times, atmospheric oxygen binds with iron to form rust, which precipitates out. But early on, free oxygen was absent. The iron stayed solubilized, lending the universal sea a metallic, poisonous tang and a profound verdant cast. The overhead vault probably wasn't cerulean either, but a foggy, rosy amber, tinted by abundant methane and CO2. The scene evoked a palette of unwell hues. A verdant sea beneath an amber firmament, sweltering, oppressive, and profoundly inhospitable to future inhabitants. The waters scalded, hovering near 100 degrees Celsius across the surface, a planetary soak just shy of ebullition. The defining absence in this primal aquatic domain was land. Vast blocks like Africa, Asia, or the Americas were yet to coalesce. Continental granite, buoyant and elevated atop the mantle, arises from fractionating denser basalt over immense timescales of plate motion. During the Hadean and early Archean eons, that mechanism was only commencing. Earth truly embodied an ocean planet, one seamless encircling sea, blanketed 95 or conceivably 99% of its girth. The sole land masses were strings of dark volcanic isles, much like today's Hawaii or Iceland, erupting ash into the air. Without any continents to serve as barriers, the ocean currents raged with incredible force. They whipped around the equator in unrestricted, lightning-quick cycles. Tides, drawn by a moon far nearer to Earth back then, reached staggering heights. Enormous tsunami-like swells battered those volcanic outcrops every 12 hours, hauling rubble back into the verdant abysses below. This was a realm dominated by savage water dynamics, and ceaselessly agitated engine of liquid and rock. Fresh water falls from the sky. The precipitation that poured down for millions of years was refined, pristine vapor. So what makes the seas saline? The salt didn't originate from above. It emerged from the stone. Early Earth's air was dense with carbon dioxide and sulfur compounds. As raindrops passed through this atmosphere, they transformed into carbonic and sulfuric acids. This corrosive downpour assaulted the volcanic formations on those islands with relentless chemical aggression. It shattered the crystalline frameworks of the rocks, extracting ions like sodium, chloride, calcium, and magnesium. These elements melted into the acidic streams and cascaded via rivers toward the ocean. This represents the grand chemical balancing act. Across billions of years, rivers have functioned as an endless transport system, scouring salts from the land masses and depositing them into the sea. Once deposited, the salt becomes confined. Water vaporizes to create fresh rain, leaving the minerals behind to build up. Through countless ages, this gradual, unseen process of chemical erosion shifted the pure acidic deluge of the Hadean era into the briny alkaline expanse we know now. Each glass of seawater holds the faint dissolved remnants of ancient mountains eroded away. The ocean transcends mere liquid. It's a fluid archive of the terrestrial past. To uncover the deeper role of this vast worldwide sea, we need to plunge beneath. We abandon the turbulent, radiation-scorched surface and plunge into the oppressive void of the deep. At the ocean bottom's rift zones where the crust thins and magma lurks near, a feature emerges that connects the rocky core to living systems: hydrothermal vents. In the pitch black, they resemble smokestacks, imposing towers built from mineral layers, expelling clouds of dark and pale plumes into the surrounding water. Yet these aren't fumes, they're intensely heated liquids. Seawater infiltrates the crust, encounters the molten material, and erupts upward, saturated with dissolved minerals. This marks the convergence of the world's primal powers: fire and water. One particular vent variety, the Lost City Fields, fosters a distinctive habitat. There, the emerging fluid is alkaline, mildly heated and laden with hydrogen. It rises through minute, porous cavities in the seafloor rock, resembling a lattice of tiny laboratories. Within this cozy, nutrient-packed obscurity, shielded from the surface's wild upheavals, the liquid performs a remarkable feat. It begins to order itself. Serving as a catalyst for intricate reactions, it stirs the planet's basic components until patterns start to form. Water isn't merely a backdrop for biology, it's the essential driver. During the Hadean and Archon seas, water served as the ultimate dissolver. It leached minerals from the vents, trapped carbon-laden particles from meteor strikes, and soaked up electrically charged vapors from the skies. It blended all these turbulent, scattered components into a worldwide mixture. This became the primordial broth. But broth suggests disorder. Water goes further by imposing form. Within the vent's minuscule openings, water envelops organic substances, shielding them and enabling buildup. It enabled amino acids, protein fundamentals, to connect. It permitted fatty acids to create spheres, early versions of cellular walls. This unfolded as an epoch-spanning series of experiments, a molecular gamble waged in shadows across vast timescales. Water supplied the protected niche, the thermal stabilizer, and the delivery pathways that let these particles collide, combine, and ultimately self-copy. The sea wasn't simply a vast pool. It was the Earth's nurturing cradle. Why water specifically? Why didn't terrestrial life evolve around liquid methane, ammonia, or silicon? The key rests in the peculiar adhesive qualities of the water molecule. As a dipole, it features opposing charges, like a minuscule bar magnet, enabling it to dissolve nearly everything, fragmenting sustenance for easy movement. Even more crucially, it enables architecture. Take DNA, life's informational double spiral. It's stabilized by water-repelling forces. Certain segments shun water and fold inward, while others embrace it and turn outward. The iconic helical twist of DNA is molded by its watery environment. Absent this aqueous tension to guide and constrain the strands, our hereditary blueprint would dissolve into disarray. Proteins achieve their working configurations solely through their interactions with water. At its core, life represents an intricate interplay of molecules immersed in H2O. We're far more than beings who simply consume water. We're entities composed from it, structured by it, and maintained by the peculiar exceptional properties of this unassuming molecule. The sea didn't merely originate us, it's embedded within us right now, binding our cells intact. Water feels commonplace in our daily existence, the most ubiquitous material around us. Yet to a scientist studying chemistry, it's an outlier. According to the rigid principles of the periodic table, liquid water ought not to persist on our planet. H2O consists of a small, lightweight molecule. Given its mass and makeup, it should mimic relatives like ammonia or methane, existing as a gas under normal room conditions. On a world such as Earth, every bit of water should long since have vaporized into steam or solidified into perpetual ice. No intermediate liquid state should be possible. Yet water defies expectations. It endures in liquid form thanks to a distinctive feature known as hydrogen bonding. Water molecules possess a clingy quality. The hydrogen in one attracts the oxygen in adjacent ones through a subtle magnetic pull. They adhere with a fleeting, ethereal hold, creating a dynamic network that resists dispersal into vapor. This unseen lattice imparts surface tension to water, enabling bugs to skim across its surface. Moreover, it's the reason water stays fluid across an enormous temperature span. Absent this intermolecular adhesion, seas would vaporize, our bloodstreams would overheat, and the globe would shroud itself in arid, poisonous haze. Water violates yet another basic principle, one so ingrained that it seldom crosses our minds. Across the physical realm, cooling causes materials to shrink. Their particles cluster more closely, increasing density and mass. Dense stone plummets through liquid rock. Solid metal drops in its molten counterpart. Water, however, reverses this. Nearing 0 degrees, its molecules form a stiff hexagonal lattice. To accommodate it, they must spread out. Consequently, ice proves lighter than liquid water. It swells and rises. This peculiarity alone accounts for our presence. Picture water following standard physical norms. Ice, denser than liquid, sinking when it forms atop seas in cold seasons. Sunlight-deprived depths would accumulate endless strata of submerged ice, immune to thaw. Seas would solidify upward from the base, encasing the world's water in impenetrable frozen masses indefinitely. Existence would suffocate or perish in the chill. Instead, floating ice creates a surface layer. This sheath serves as thermal insulation, conserving warmth beneath and preserving subaqueous liquidity, sufficient for survival amid the severest glaciations. Water's third remarkable feat involves its handling of thermal energy. It boasts an extraordinarily elevated heat capacity. It's resistant to change. Enormous energy input is required to raise its temperature, and once heated, it clings tenaciously to that warmth. In contrast, stone is capricious. Arid regions without water experience drastic diurnal shifts. Scorching midday highs plunge to sub-zero nights. Stone bakes, then chills abruptly. Oceans, however, function as Earth's climate regulator. They serve like vast heat reservoirs. By day, they soak up intense solar rays without reaching boil. Overnight, they gradually emit stored warmth into the air, averting nocturnal deep freeze. Lacking oceanic tempering, our planet would endure extreme, deadly fluctuations. Tropics would scorch like furnaces, while poles plummeted to near absolute zero. Oceanic flows, the Gulf Stream and the Kuroshio, form the circulatory network, redistributing this energy, channeling tropical heat northward. We inhabit the mild mid-latitudes forged by this worldwide cooling mechanism, oblivious to water's thermal persistence, shielding us from cosmic emptiness. We often view the sea as an unchanging basin, perpetually brimming. In truth, its bed operates like a shifting belt. In profound chasms such as the Mariana Trench, Earth's crustal plates converge. One subducts under another, descending into the scorching gooey mantle. Through this subduction, as seafloor rock submerges, It hauls ocean water along, not cascading like sink drainage, but bound chemically into the bedrock. Seafloor stones infused with eons of compressive hydration drag immense volumes downward into the planet's fiery core, trillions of tons in total. Fresh analyses of seismic data indicate that the Mariana Trench engulfs triple the water volume we once estimated. This process unfolds gradually and without fanfare. Our world is gradually absorbing its vast seas, drawing them into the profound depths where they may have originated eons ago. Yet Earth operates in loops rather than as a graveyard. Whatever descends must eventually ascend. The moisture carried downward by sinking tectonic plates doesn't remain entombed indefinitely. Within the mantle, as temperatures climb, that water gets released under pressure. It ascends, blending with magma to power the dramatic eruptions along the ring of fire. Occasionally, though, it reemerges in an unexpected guise. Across the Pacific seafloor lie peaks that erupt not with lava but with sediment. Known as cold seep mud volcanoes, these imposing formations arise from the expulsion of pulverized stone and high-pressure fluids originating in subduction regions. They serve as outlets in the globe's subterranean piping network. From these emerge liquids confined beneath the surface for immense spans of time. O2O that has journeyed through the planet's core. This concealed loop, from precipitation to sea, then into the mantle, and returning via eruptions, functions as a steadying mechanism over vast timescales. It guarantees that even as surface waters fluctuate in volume, the Earth as a whole avoids desiccation. Beyond mere circulation, this subsurface H2O plays a vital role in sustaining the planet's vitality. Scientific insights into geology highlight that plate tectonics, the movement of land masses, the erection of ranges, the renewal of the outer layer, is a phenomenon exclusive to our world within the solar system. Consider Venus, a body of comparable dimensions and makeup. Its exterior forms one immobile, unchanging cover. No plates shift there. The explanation: once more, it's H2O. In the lower crust and uppermost mantle, water serves as a crucial lubricant. Its presence weakens the solidity of stones. It diminishes melting temperatures and eases the drag across enormous slabs of lithosphere. Absent this hydration, the crust would turn arid, inflexible, and immobilized. Land masses would halt their wanderings. Carbon renewal would cease. Volcanic activity would fade. The sphere would evolve into a geologically inert body, akin to Venus. It's the moisture greasing the mechanisms of the inner Earth that permits continental drift. The solid terrain beneath our feet remains dynamic solely due to its buoyancy atop a concealed stratum of dampened lithosphere. The seas aren't merely ecosystems. They function as the vital lubricant for the entire world. To truly grasp the odd allure of our planet's exposed waters, contrast them with rivals. For ages, we assumed Earth stood alone as the solar system's watery haven. That assumption proved false. Other bodies of water exist, concealed from view. Around Jupiter circles Europa, an orb cracked and encased in pale frost. Near Saturn revolves Enceladus, a diminutive, shimmering ice sphere. Visually, they appear lifeless and iced over. Gravitational dynamics paint another picture. As they trace paths around their colossal gaseous hosts, powerful tidal pulls warp and elongate them. Such internal rubbing produces warmth at their centers. This warmth thaws the frozen layers from below. Under Europa's kilometers-thick, unyielding icy barrier lies a briny liquid expanse potentially reaching 60 miles in depth. It holds a volume surpassing the sum of all Earth's seas. Yet it's a covert body of water, existing in perpetual night, isolated from sunlight, celestial lights, and any gaseous envelope. It's an expanse confined in a world-scale cauldron, heated and laden with minerals, but eternally barricaded by its frozen ceiling. Such contrasts underscore Earth's remarkable exceptionality. Across the cosmos, liquid H2O typically resides concealed, shielded under layers of stone or frost. Subsurface seas could abound, but an exposed one, unprotected like ours, stands out as exceptional. Our waters bask openly under the heavens. They mingle with breezes to form swells. They vaporize to generate downpours. They mirror solar rays. This accessibility renders our world susceptible. Lacking a robust icy shield, our seas depend wholly on the fragile equilibrium of the air layer and protective magnetosphere to prevent evaporation into the void or solidification into ice. We tread a precarious path. The splendor of the Pacific or Atlantic stems from their vulnerability. They act as the world's breathers, swapping vapors with the sky, shaping weather patterns, and fostering the turbulent, illuminated realms where intricate organisms developed vision to behold the cosmos. The concealed seas of Europa might harbor organisms, yet those would remain ignorant of any skyline. Water's tail extends beyond planetary structure. It persists within us. When organisms first ventured from the seas onto arid shores hundreds of millions of years back, they encountered peril. They were abandoning their cradle. Terrestrial conditions brought arid winds and intense solar exposure. For endurance, they carried the sea internally. They incorporated the forsaken milieu into themselves. You embody this primordial brine. The average human form consists of about 60% H2O, though not the pure variety. Your bloodstream's fluid, perspiration, and ocular secretions carry salt. The salt levels in your bodily fluids closely mirror the salinity of those ancient primordial seas where life originated. Humanity never fully abandoned the water. Instead, we fashion suits of flesh and skeleton to transport it everywhere we go. With each heartbeat, your veins circulate a subtly altered remnant of that primordial ocean. We're essentially mobile, respiring aquariums, preserving the echoes of deep time within our very biology. Delve deeper beyond the organs and tissues, right down to the cellular scale, and the reality persists. A cell's interior, known as cytoplasm, forms a gel-like watery medium, an ocean in miniature. The essentials of existence, from DNA and proteins to mitochondria, can't operate in emptiness or solidity. They drift freely. These molecular components hover in suspension amid water, influenced by thermal flows and chemical forces akin to those driving ocean tides. A protein's crucial folding, the exact configuration enabling its role, emerges from its engagements with surrounding water molecules. Nerve impulses travel as ionic streams through hydrated pathways. At its core, life amounts to an intricate, structured ballet involving water. Remove the solvent, and the performance halts. The solid ground beneath us deceives. On a cellular plane, we're perpetually immersed. Now picture the water in that glass by your bedside. It appears straightforward and transparent, yet each droplet carries a saga, stretching across the solar system's full lifespan. Born from a star's explosive demise, solidified in the frigid outer nebula, and delivered to Earth via a stony asteroid amid the late heavy bombardment, it has circulated through our world for 4.5 billion years. It has risen as vapor in the Hadean skies, locked into a glacier that ground across continents, been ingested by dinosaurs or exhaled through towering ferns. It has plunged into the mantle's depths only to erupt from volcanic vents. The liquid you sip isn't fresh, it's endlessly reused, refined through the planet's vast evaporation rain distillation. Those same atoms fell as precipitation on the young Earth's scorching surface. Water alone endures as the Chronicle's sole observer. Yet this narrative won't endure indefinitely. Earth functions as a bounded system, though not airtight. Up in the sparse upper atmosphere, solar ultraviolet rays dismantle water molecules, retaining oxygen while the lightweight hydrogen slips free from gravity's grasp, vanishing into the cosmos. This phenomenon, atmospheric escape, acts as a gradual, unseen seepage. Moment by moment, our planet forfeits a minuscule portion of its water to emptiness. Across eons, it will parch the world. As the sun matures and intensifies, rising temperatures will hasten the depletion. Seas will vaporize, atmospheres erode, leaving Earth a barren, lifeless stone, reminiscent of Mars or Venus. Our blue orb represents just a fleeting moist interval in a planet's protracted arid existence. We're amid water's peak era. Still, that conclusion lies distant indeed. Presently, the loop persists. Solar warmth lifts ocean water into vapor, clouds gather, and precipitation descends. This rhythm pulses through the biosphere. Tune into rain pattering on the pane. It's a noise echoing across 4 billion years of planetary history. It's the atmosphere tempering stone, the sea reclaiming terrain. That resonance captivates us. The roar of surf on beaches or the persistent patter of storms stirs profound, innate comfort. Maybe it's because, fundamentally, it's the echo of our birthplace. Born of the waters, we're ocean refugees dwelling on arid expanses, harboring personal seas inside. Water's murmur binds us back to roots, to epochs when we were mere protocells adrift in the warm, reactive soup of nascent Earth. Thus concludes the tale of water's beginnings. We've followed one droplet's path from a comet's fiery core to the serene vessel at your side. The loop seal's shut. For some listeners, I trust this voyage's cadence has already lulled you. May the perpetual downpour usher you toward profound, unbroken slumber. If you're easing away, surrender, you're secure. Yet if you're lingering, if quiet hasn't claimed you, should your thoughts still roam the hushed night and sleep eludes, I've another tale to share. A shift in focus. We've lingered on water, but overlooked its concealed depths. An enigma dwells not within the liquid, but beneath. So if you're accompanying me, let's prolong the shadows. In imagination, we'll recede the tides and peer at the secrets Earth prefers to bury. Our exploration of these vanished territories kicks off in the immense, apparently barren reaches of the South Pacific. Glance at a typical world map, and you'll spot Australia, with New Zealand's islands emerging thousands of miles eastward. In between stretches just endless azure ocean. It appears as an emptiness, a void etched onto global charts. Yet should you drain away that sea, if you could somehow empty the Pacific, you'd uncover a sight that challenges every textbook on geography. New Zealand isn't simply a string of islands. Rather, it's the towering summit of a submerged colossus. Hidden under the surface sprawls a massive terrain, almost two-thirds as large as Australia. It features rugged peaks, deep basins, and elevated plateaus. This forms a unified slab of continental rock that split off from the supercontinent Gondwana 80 million years ago. Researchers name it Zealandia, or in the indigenous Maori tongue, Te Riu a Maui. It qualifies as Earth's eighth continent. But in contrast to its counterparts, Zealandia failed to stay afloat. Its tale unfolds as a dramatic geological downfall. As it separated from Australia and Antarctica, the crustal layer got pulled and elongated. It acted like warm taffy stretched to its limits. Gradually, it grew ever more slender. With that thinning came a loss of lift. It turned weighty. The mantle below could no longer bear its load. 23 million years back, the waters surged forward. Low-lying valleys submerged initially, followed by the flatlands and eventually the rises. 94% of the land vanished beneath the waves, fading into oceanic hush. We need to envision the realm that slipped away. Prior to its descent, Zealandia floated as a verdant platform. Dense, ancient Araucaria woods, enormous ferns, and singular evolutionary marvels blanketed it. Since it detached from Gondwana, prior to mammals' emergence, it served as a haven for avian and reptilian life. Dinosaurs could have persisted there a bit longer. The Tuatara, a reptile representing the final remnant of a group predating dinosaurs, still roams the sparse summits poking above the sea today. As we navigate the Tasman Sea, we're gliding atop a forgotten domain. We're passing over petrified woodlands and primordial stream courses untouched by sunlight for 20 million years. It's a spectral landmass, a dormant behemoth lurking right under our hull, biding time in obscurity, while Zealandia succumbed to the profound quiet pulses of deep time. Eons before any gaze beheld it, other regions fell victim to the span of human history. To discover one of the most evocative and eerie of these submerged realms, we head to the chilly, overcast, and stormy expanse of the North Sea, the watery divide now parting Great Britain from continental Europe. In our era, this is a harsh, unwelcoming body of water, dotted with drilling platforms, turbine arrays, and sturdy industrial spires. It seems enduring, a wall of brine and gales. Yet this divide is recent, merely 8,000 years past, a mere instant in Earth's timeline. This sea was absent. In its place bloomed an Eden. This was Doggerland. Far from a mere causeway or skinny pathway for transit, it was an expansive, fertile, and teeming subcontinent. It pulsed as Europe's genuine core. Picture an unbroken sweep of undulating tundra, marshes, and fertile meadows, linking England's chalky bluffs straight to the level shores of Denmark and the Netherlands. The Thames didn't spill into the ocean. Instead, it merged as a feeder into the Rhine, creating a colossal pan-European waterway that meandered slowly over the expanses before pouring into the Atlantic. Vast packs of woolly mammoths, reindeer, and feral equines wandered freely, foraging across grounds now smothered beneath 50 meters of oppressive brine. It may well have been the prime hunting territory across the northern hemisphere, a realm of plenty sustaining countless Mesolithic forebears. Our knowledge stems not from folklore or tales, but from the sea's occasional returns of its plunder. For ages, trawlers from the Dutch and English coasts, hauling weighted seines along the seafloor, have dredged up items alien to the depths. Beyond fish, they snare darkened mammoth ivory. They retrieve woolly rhino crania and oversized Irish elk horns. And, most eerily, they haul in human relics. Harpoons fashioned from bone, flint blades, and fragile skeletal remains emerge. Echoes of people who thrived, bonded, and perished on soil turned seabed. These remnants mark the rubble of a submerged society. Solid, weighty evidence that amid today's surging tides once rose the glow of hearth fires. Doggerland's demise played out as a drawn-out cataclysm spanning thousands of years, with the vast ice caps of the latest glacial epoch starting their ultimate thaw. Worldwide oceans swelled steadily. Inch by inch over lifetimes and eras, the tide advanced. Broad meadows morphed into briny bogs. Those bogs evolved into intertidal zones. The woodlands perished, their root systems tainted by the advancing salinity, resulting in eerie remnants of petrified tree stumps visible only during the lowest tides along England's shoreline. The inhabitants of Dogland, victims of a climatic disaster, had no choice but to flee to elevated terrain, gradually relocating to the uplands that would later form Britain and the Netherlands. Yet the decisive strike came without warning, abrupt, ferocious, and horrifying. Approximately 6,200 BC, a tremendous seismic upheaval struck offshore from Norway. An enormous portion of the continental shelf gave way in what's called the Storegga Slide. This subaqueous avalanche displaced an unimaginable mass of stone and silt, unleashing a colossal tsunami. A surge of water, possibly reaching 20 meters, barreled through the North Sea. It crashed into the soggy, low-elevation leftovers of Doggerland with explosive power. The impact ravaged the shores, submerging the surviving islets and obliterating human communities in mere hours. As the waves pulled back, the terrain lay contaminated, fractured, and mostly vanished. Britain broke free from the European mainland. The core region was wiped out. Doggerland faded into legend, its echoes caught in the seabed's sediment and hush, ready for a trawler's line to haul its mysteries into daylight. Deep in the south, amid the stark, gale-ravaged expanses of the Indian Ocean, equidistant from Africa, Australia, and Antarctica, rests yet another submerged giant. Enter the Kerguelen Plateau. On today's charts, you'd spot only the small, rugged Kerguelen Islands, sometimes dubbed the Desolation Islands. These are barren, vegetation-free crags, relentlessly assaulted by the relentless gales of the polar circle. But they represent merely the peaks of a vast underwater microcontinent, spanning thrice Japan's area. In contrast to Zealandia, a shard of ancient continental bedrock, Kerguelen emerged from volcanic fury. It's a sprawling igneous region, an immense buildup of lava rock forged by a mantle hotspot that spewed forth relentlessly over millions of years, forging fresh territory amid the widening sea. About 100 million years back in the Cretaceous era, this plateau wasn't some shadowy depths. It stood as a thriving, foliage-rich connector. Samples extracted from its subsea bed uncover a surprising past. Hidden under deposits of oceanic slime lie remnants of old earth, charred wood, and preserved pollen grains. These tiny indicators reveal that the submerged territory once supported thick groves of ferns and cone-bearing trees, akin to today's cool climate woodlands in New Zealand or Patagonia. It served as a verdant haven, a vital link for dinosaurs and primitive mammals traveling from India to Antarctica, prior to the continents pulling too distant. Today, it's a quiet submersed plain, eroded by profound sea flows, a flooded realm of basalt, home solely to abyssal creatures and the specters of woods long submerged. Tales of these submerged realms aren't just historical footnotes. They foretell what's ahead for us. We often treat the world's outline as an unchanging artwork. We etch boundaries. We erect seaside metropolises. We lay roads right by the water's edge, assuming the ground endures forever. Geology reminds us, though, that the shore isn't a steady edge, it's a fleeting, shifting frontier. We're in an interglacial phase right now, a short thaw amid the glaciers. Yet, as we've seen, the glaciers are thawing once more. The pattern of sea encroachment, the sea's advance, restarts. Viewing our current planet through a geologist's gaze shows us the impending vanished lands, Florida's slender limestone spur, the sprawling deltas of Bangladesh and the Mekong, the chain of Pacific atolls. These are fleeting formations in Earth's vast timeline. They're as short-lived as a beach fort at ebb tide, with seas swelling and recapturing icebound moisture. These areas will mirror Doggerland's End, our gleaming towers of metal and glass basking under the sky, will turn into submerged relics overtaken by reefs and seaweed. The sea bides its time. It has seized lands in the past, and it will do so anew. The very liquid we rely on for life is the same that lurks to swallow the soil. We raise our societies at the monster's brink, praying it slumbers on. Earth's chronicle, however, murmurs that the monster stirs in time. Yet water isn't our sole guardian, or the only force stirring below. Far beyond the air layer, stretching thousands of miles into space's dark void, an unseen, radiant shield enables Earth's intricate life. That's the magnetosphere. This immense magnetic bubble arises from the turbulent sea of liquid iron, swirling deep in the planet's outer core. It serves as a protective barrier, ripping into the lethal solar wind and repelling the cosmic rays that could otherwise erode our atmosphere, evaporate the seas, and render the surface lifeless. Absent this unseen safeguard, our world would resemble a barren, crimson wasteland akin to Mars. We often view this barrier as steadfast, consistent, and indestructible, yet reality proves otherwise. At present, a vulnerability exists in this protection, an expanding gap in the planet's defensive shell. Spanning from Brazil's shoreline over the enormous South Atlantic Ocean and extending to southern Africa's coastlines, lies an area called the South Atlantic Anomaly. In this zone, the planet's magnetic field is markedly and puzzlingly feebler than in any other part of the world. It's like a spectral void. Here, the Van Allen radiation belts, those loops of high-energy charged particles trapped by the magnetosphere, plunge perilously close to the upper atmosphere. From a ship's deck, the heavens appear ordinary to our eyes. Yet for the delicate instruments powering our society, this spot is space's version of the Bermuda Triangle. As satellites in low orbit traverse it, they face a barrage of unchecked cosmic radiation. Systems falter and fail, information gets garbled. Even the Hubble Space Telescope automatically deactivates its delicate imaging instruments while crossing this zone to prevent damage from the cosmos's harsh light. This breach is an enlarging rift in our safeguards, a tangible sign of upheaval far below in the Earth's core that we're only starting to comprehend. That subterranean iron sea is unsettled, brewing a tempest that's punching through the magnetic canopy overhead. The South Atlantic Anomaly isn't a standalone issue. It's an indicator of broader unrest on a global scale. Our compasses, airport layouts, and charts all rely on the idea that north stays put. But the magnetic North Pole isn't stationary. It's a wanderer. For ages it shifted gradually through the Canadian Arctic, ambling like a sluggish vessel. Then, in the 1990s, a shift occurred. The pole picked up speed. Today, it's hurtling over the Arctic Ocean, departing Canada for Siberia at more than 30 miles per year. Its rapid pace has forced an early revision of the world magnetic model, the core math behind navigation for everything from phones to subs, just to match the movement. Yet this motion pales against the planet's potential for extremes. Clues, etched in the magnetic orientations of minerals within old lava, reveal a chilling tale. The poles haven't merely wandered, they've inverted. Over Earth's long past, the magnetic engine has turned erratic many times. The dipole, that distinct north-south alignment, disintegrates. The field drops to mere slivers of its power, with extra poles emerging across the planet. South turns to north, north to south. This phenomenon is a geomagnetic reversal. The most recent full one was about 780,000 years back, though briefer flips happened later. The Lachamp event, some 42,000 years ago, reduced the field to only 5% of today's intensity. Back then, the protection all but disappeared. We can't precisely picture a complete reversal from surface level, but simulations are eerie. It wouldn't happen overnight, more like ages or eons of magnetic disorder. In that period, the atmosphere would transform. Auroras, now mostly polar, would spread equatorward, illuminating equatorial nights. Imagine shimmering veils of vivid green and crimson, dancing above Egypt's pyramids or the Amazon's rainforests. It would be an era of stunning spectacle laced with deep peril, a phase when the hidden barriers fall, exposing the planet to the sun's raw, unrelenting assault. The South Atlantic weakness hints that the core is gearing up for another major reversal. As we monitor the fading shield overhead with concern, we're still mostly in the dark about the strange realm buried underfoot. For generations, scientists believed life was confined to the surface, a delicate verdant layer on the crust, wholly reliant on solar power. But lately, ocean borings and deep mines slicing kilometers into continental rock have uncovered a startling reality. Life doesn't end at the skin of the Earth. It plunges far below. Researchers have extracted samples from 3 kilometers under the seabed, ancient solid basalt entombed for eons, and discovered it buzzing with organisms. These aren't beings of sunlight. They're the deep dwellers of the interior. These microbes consist of bacteria and archaea, residing not within caverns or subterranean pools, but inside the tiny water-saturated voids within the dense rock. They inhabit an unending realm of oppressive gloom, enduring forces that could crush a submersible and heat levels capable of vaporizing surface water. Welcome to the deep biosphere, a revelation that has utterly transformed our view of the world. Projections indicate this underground domain is immense enough to harbor a greater total mass of life than the combined weight of all surface forests, wildlife, and people. Our planet isn't merely a stone adorned with organisms. It's a living entity, infused with a concealed web of biology that plunges several miles into its outer shell. Yet the existence below starkly contrasts with that above. Surface life pulses with urgency, a desperate scramble for fuel. A microbe in a lab dish or shallow pool could replicate every 20 minutes. Down in the deep biosphere, though, supplies are meager. Without sunlight or influxes of nutrients, these beings subsist on the subtle chemical power from the planet's gradual cooling or the leisurely breakdown of uranium and nearby minerals. With energy so sparse, they've adapted to a glacial pace. Picture them as the undead denizens of the bedrock. Research on these subsurface bacteria reveals they don't reproduce in mere hours or weeks. A lone cell might require centuries, millennia, or even 10,000 years for a single split. They linger in a near-dormant metabolic haze, teetering on the edge of vitality and oblivion. They're like stone-carved effigies, thriving or surviving on a time frame that flirts with eternity. They've endured there for eons, confined in rocky prisons, unmoved by the dinosaurs' demise, the grip of glacial epochs, or humankind's ascent. To them, the surface's turbulent drama is but a momentary tremor. They hold true dominion over the globe, the shadowy essence of life's fabric, biding their time amid the minerals as eras shift. This concealed subterranean chronicle prompts a query that veers into speculative territory, though it's pondered not by fringe theorists, but by esteemed climate experts and cosmic scientists. Dubbed the Silurian hypothesis, it's a conceptual exercise that exposes flaws in how we gauge chronology. We presume our primacy. Gazing at our urban sprawls, innovations, and worldwide impact, we deem ourselves the ultimate apex of cognition here. But Earth clocks in at 4.5 billion years. Our industrialized society has lasted roughly 300 years, a sliver so minuscule, it's practically invisible in stats. The hypothesis poses a straightforward, disquieting probe. If an advanced society thrived on Earth eons ago, predating us by millions of years, could we detect it? Suppose a Triassic reptile lineage or a Paleocene mammal group erected metropolises, consumed fuels, and crafted creations. Would remnants endure to signal their presence? Instinct says yes. We admire enduring icons like the Giza pyramids, China's Great Wall, or Manhattan's towers, convinced they've etched an eternal signature onto the terrain. Yet to the planet, our era is just a transient overlay. Earth functions as a merciless recycler. Let's play out the scenario. Suppose humankind evaporates overnight. What becomes of our tangible legacy? We boast of our feats, but the environment is unhurried and unyielding. In centuries, dampness and corrosion will corrode our metal frameworks, toppling them into heaps. The concrete, bereft of its steel supports, will fracture and dissolve into grit. Over millennia, regrowing woodlands' roots will pulverize our settlements to powder and entomb them beneath accumulating earth. But erosion delves far beyond the surface. The planetary shell is dynamic. Across millions of years, the plates beneath us will shift, fold, and liquefy. Land masses will reform. Ice sheets will abrade landscapes to bare stone, wiping clean all traces atop. The fossil archive, our key resource, isn't a flawless archive. It's a tattered volume. Sure, we possess dinosaur relics, but they represent an infinitesimal sliver of all creatures that once roamed. The chance of any particular kind preserving as a fossil nears nil. Should a sophisticated culture endure just 10,000 years, the length of our recorded past, before crumbling, it'd register geologically as a sediment stratum thinner than paper. It'd blend seamlessly with ordinary occurrences. The remnants of a grand realm don't withstand profound epochs. If the statues, structures, and devices have all been reduced to powder, what endures? In what ways could we uncover traces of a vanished society? Experts proposing the Silurian hypothesis argue that we ought to search not for artifacts, but for chemical traces. We should seek out the very markers we're imprinting today. When societies consume vast quantities of fossil fuels, they alter the atmospheric carbon profile, unleashing a particular light isotope, carbon-12, that seas take up and embed in sediments. Geologists, eons hence, won't uncover our vehicles, yet they'll detect this surge in carbon isotopes within the strata. They'll notice an abrupt, baffling rise in the world's thermal history. They'll encounter strata rich in technofossils, odd artificial compounds such as plastics, and enduring synthetic substances that linger for geological ages. They could even stumble upon deposits of plutonium-244, an artificial radioactive element, absent from nature, producible solely through nuclear fission. Such are the hallmarks of industrial activity. They're what persists over immense timescales. This is the point where the idea shifts from mere speculation to an enigma. Examining Earth's deep geological past reveals irregularities. We spot occurrences that eerily mimic our own Anthropocene era. The most renowned is the Paleocene-Eocene thermal maximum, or PETM. About 56 million years back, the globe experienced a swift, severe, and widespread heating episode. Temperatures soared, seas turned acidic, and, crucially, a huge, unexplained influx of carbon entered the air. The conventional account points to natural causes, like enormous volcanic outbursts or methane hydrates erupting from ocean floors. That's probably accurate. Yet the evidence remains unclear. The velocity and scale of the carbon discharge in the PETM strikingly resemble our ongoing fossil fuel combustion rates. We're not claiming some ancient culture triggered it. Still, the Silurian hypothesis imparts a sobering insight. We can't rule out that possibility. It implies that societal development may not climb steadily like a staircase, but recur in loops. A repeated planetary surge that the world endures, erases, and maybe permits once more. The quiet of ancient rocks might not signal absence. It could just conceal the lingering emissions from a lost dominion. Yet the planet doesn't merely deposit chemical clues. It vocalizes actively. Often we navigate daily existence oblivious to Earth's whispers. We catch the breeze, urban clamor, or fellow humans' chatter. But for decades, reports have surfaced, from New Mexico's barren expanses to England's misty shores, indicating the globe itself emits a tone. Dubbed simply the hum, it's a persistent, low-pitched buzz teetering on the edge of audibility. Listeners liken it to a far-off diesel motor, rumbling idly, or the thrum of some colossal unseen apparatus buried far below. It penetrates barriers. It robs sleepers of rest, pulsing through their frames. An elusive auditory specter that evades ordinary recording gear. Long dismissed as tinnitus or fancy, it's now deemed genuine by researchers. This is Earth's inherent hum. It stems from the ceaseless force of waves pounding continental edges, generating subtle seismic ripples across the rigid lithosphere. Our world resonates like a struck gong, quivering at an infrasonic pitch that's sensed rather than audible. It underscores that the soil underfoot isn't inert. It's perpetually quaking with the vigor of its oceanic shroud. Another rhythm arises not from the soil, but the sky. This is the globe's electric cadence. The gap between ground level and the ionosphere high overhead forms a planetary electromagnetic chamber. It mirrors the resonance chamber of a string instrument. Each moment, countless lightning bolts strike worldwide. These function as mallets on a chime, setting the aerial enclosure vibrating. Known as the Schumann resonance, its bass tone sits at 7.83 Hz. This is a persistent, encircling standing wave, an unseen beat enduring since the atmosphere formed. Curiously, 7.83 Hz matches the alpha and theta brainwaves in humans, realms of calm contemplation and drowsiness. Onset. We developed amid this electromagnetic immersion. Our physiology aligns with the world's own tempo. We're intertwined with the planet. Our neural wiring syncs to its ionospheric throb. It hints at a profound unseen bond, a resonance between psyche and environment we're scarcely starting to fathom. As this extensive voyage draws to a close, the scattered elements of the enigma coalesce into one stunning whole. We've examined the waters that balance the climate. We've explored the magnetic barrier safeguarding the atmosphere. We've delved into the subterranean life teeming through the crust and the relentless patterns of ruin and renewal that reshape the terrain. Stepping back to observe these mechanisms operating together, our planet ceases to resemble mere stone. It begins to resemble a living entity. Enter the Gaia hypothesis. It posits Earth as an intricate, self-sustaining entity that sustains the essentials for existence. Just as a biological form regulates its heat and composition, the volcanoes serve as its outlets, the seas as its circulating fluid, the air as its respiratory organ, the magnetic layer as its protective covering, and we might be its neural cells, the initial segment of this immense global form to gain awareness and stir into sentience. We represent the means by which Earth perceives its own being. What began as a quest to uncover the origins of water revealed it as an interstellar wanderer, enduring the Hadean inferno and molding vast landmasses. Yet in following its path, we discovered our own essence. The particles composing your form were once embedded in the meteorite that delivered the oceans. The salinity in your veins recalls the primordial sea. The neural pulses in your mind resonate with the ancient thunderbolts overhead. We're no mere travelers aboard this vessel. We embody the vessel itself. We constitute the fleeting forms that water and stone assume to enable motion, respiration, and contemplation. Earth's chronicle isn't confined to bygone eras. It unfolds within you at this very moment. You form the ongoing installment of the tale. You embody the world's recollections incarnate. With that, the Odyssey concludes. The loop reaches fulfillment. The waters have descended from the heavens, etched the earth, and retreated to the depths. Submerged landmasses rest in obscurity. Concealed microbes linger within the rock, while the world intones its gentle, persistent song. Release your hold now. You're woven into this expansive, enduring, and wondrous framework. From your first breath, Earth has cradled you, and it will sustain you into the darkness. The quiet surrounding you isn't void. It's brimming with vitality, with legacy, with cosmic wonders. Allow the world's cadence to transport you. Permit the eons to flow across you. Good night.